In our last lesson, we described 2D vectors in two different ways. The polar form describes a vector as a magnitude and a direction. We use angles measured counterclockwise from the x direction to represent the direction. The second way of describing a vector is the Cartesian form. The Cartesian form describes the vector with an x and a y component. We also learned how to use trig formulas to convert vectors between polar and Cartesian forms. In this lesson, we're going to learn how to do addition and other arithmetic operations on 2D vectors. Let's start with an example. Suppose my dog runs 50 meters with a direction of 70 degrees. Then another 35 meters with a direction of negative 50 degrees. What would my dog's total displacement be? We can start by sketching out the motion. The first part of the dog's motion has a direction of 70 degrees. Straight up along the y-axis would be 90 degrees. The dog's running a little bit to the right of that. Then he's going to turn to a direction of negative 50 degrees, which is kind of diagonally down and to the right. And he's going to run for another 35 meters. So that's going to put him somewhere around here. Now there are two ways we can calculate the total displacement. The first method we're going to look at is the graphical method, where we're going to determine the displacement simply by drawing an accurate vector diagram of the motion. And then later on, we're going to learn about the component method, which involves less drawing and more calculations. The first part of the displacement is a vector with a magnitude of 50 meters and a direction of positive 70. So to draw this, we want to draw it accurately, so we're going to use graph paper. And we're going to use a protractor and a compass and ruler to make sure that our drawing is as accurate as we can make it. So first I'm going to position my protractor right on the origin, which I'll take to be the starting position or the initial position of the dog. I'm going to measure out 70 degrees and I'm going to put a little mark so I know where 70 degrees is. Then, after moving my protractor out of the way, very lightly in pencil, I'm going to draw a line that shows the 70 degree direction. Now we need to measure out a distance of 50 meters. We can use the compass from our geometry set, or we could just make marks along a sheet of paper, or we could use a string, anything that will allow us to measure the length. Now remember, our vector diagram is a scale drawing, so we have to account for the scale of the diagram when we're measuring lengths. So essentially I'm going to use the axis as a ruler. Also remember from last lesson that we have to use the same scale on both the x and the y axis. So we can use either axis, it shouldn't make a difference when we're measuring out the lengths. I've marked off a length of 50 along the x axis, and then I'm going to take that recorded length and I'm going to measure off 50 meters along the direction of the vector. Now that I know where the tip of the vector is, I can draw in my arrow, which represents the first part of the dog's displacement. So that's the 50 meters, that's the length of that arrow, and 70 degrees is the direction, which is the angle between the arrow and the x-axis. Now the second part of the motion is a displacement with a magnitude of 35 meters and a direction of negative 50 degrees. So I'm going to flip my protractor upside down. I'm going to position the protractor at the tip of the first vector. Then I'm going to measure out 50 degrees, and just like before, I'm going to put a little mark so I know where the 50 degrees is. I'm going to draw a very light line in pencil showing me the direction negative 50 degrees. And now I'm going to take my compass or my piece of paper, whatever I'm using to measure lengths, and I'm going to measure out 35 meters. And once I've measured out the correct distance, now I can draw an arrow representing the second displacement. So the first arrow starts from the origin. It's 50 meters long with a direction of 70 degrees. The second arrow starts from the tip of the first arrow. It's 35 meters long with a direction of negative 50 degrees. So these two blue arrows, drawn tip to tail, represent the motion of the dog. Now we want to know what the dog's total displacement is. So you might be inclined just to take the 50 meters and the 35 meters and add them together and say that the dog moved 85 meters. Well, that 85 meters, that's the distance that the dog traveled, right? 50 meters, and then another 35 meters is 85 meters. But displacement is different than distance. In physics, displacement is always measured in a straight line. The path that the dog actually follows isn't really of any concern when we're measuring displacement. All we're concerned with is where they start and where they end up. So to illustrate the displacement, I'm going to draw in a third arrow. This one's going to start at the origin, which is where the motion began. It's going to end at the tip of the second vector, which is where the motion ended. Now you should be able to see from the diagram that if I were to measure the magnitude of the displacement, the length of that red arrow, it's going to be quite a bit less than 85 meters. Because the dog followed an indirect path, the distance that he traveled is going to be quite a bit bigger than the magnitude of his overall displacement. Now that we've made an accurate vector diagram, we can use the diagram to measure the total displacement. The tail of the displacement vector is at the origin. The tip of the displacement vector is just under 40. So we know that the x component of the total displacement is around 40 meters. If we look at the y component, again we start at the origin. The y coordinate of the tip of the vector is just over 20. So we can say that in Cartesian form, the total displacement has an x coordinate of approximately positive 40 and a y coordinate of positive 20. We can also make measurements in polar form. So again, taking our compass or our piece of paper or whatever it is that we're using to measure lengths, we will line up our measuring device with the vector. And once we've measured the length, we'll hold it up against the axis. And we can see that it's just under 45, maybe about 44 meters would be the magnitude of the displacement vector or the length of this red arrow. And again, using our protractor, we'll line it up at the origin, which is where the tail of the vector is, and we can see that the direction is approximately 27 degrees. So in polar form, the total displacement is approximately 44 meters with a direction of positive 27 degrees. Let's focus now just on the x motion. The first part of the displacement, the 50 meters with 70 degrees for the direction, if we look at just the x component, we can see that it starts at the origin and its x coordinate up by the tip of the vector is between 15 and 20. It's about 17 meters. So we can illustrate the x component of that displacement by drawing a vector from 0 to about 17 along the x-axis. If we do the same thing for the second part of the displacement, it's starting at about 17 for its x-coordinate and it's ending just under 40. So if we draw a second displacement vector along the x-axis, that's what we get. So these two green arrows represent the x components of the two displacements, and it's those two arrows added together that go from 0 to just about 40, which gives us our total x component. Now what's important about these two green arrows is that we don't have to rely on measurements. If you recall the last lesson, we used trigonometry formulas to calculate the components of a vector. Let me move the second x component out of the way, and then let me draw the y component as well. So as you learned in the last lesson, if I draw the x component and the y component of a vector, it's going to form a right-angled triangle with the vector itself. And because it's a right-angled triangle, we can use trigonometric formulas like sine, cos, tan, or the Pythagoras formula in order to do some calculations. So let's calculate this 17 meters that we estimated from the diagram. Let's now calculate it using the trigonometry formulas and see if we can get a more accurate answer. I've made a table here so that we can record our results for our x calculations and for our y calculations separately. So let's start with our 50 meter vector with a 70 degree direction. When we calculate the x component, we use the cosine formula. So on my calculator, I'm going to type 50 meters and I'm going to multiply by the cosine of 70 degrees. And that's going to give me my x component, which is about 17.1. So that's an agreement with the 17 meters or so that we estimated, but the calculation is far more accurate than the estimate we get just by reading off the graph. Let's look at the y component as well. To calculate the y component, we're going to take the magnitude and multiply by the sine of theta. So if I type in 50.0 times the sine of 70 degrees, I get, rounded to 3 significant digits, 47.0. So that's going to be my y component for the first part of the displacement, which I'm calling d1. So looking at this right angle triangle here, 17.1 is the adjacent side, 47.0 is the opposite side, and of course the hypotenuse was 50 meters. That's information that we started with. Now we can do the same thing for the second displacement vector. So we know it has a magnitude of 35 meters in a direction of -50. And again, the x and the y components are going to form a right angle triangle. And using the trigonometric formulas, we can calculate the x component is going to be 35 meters multiplied by the cosine of -50, which gives us 22.5 in the positive direction. So that would be the length of this green arrow here. Then doing the same thing, except changing cosine to sine, in order to calculate the y component, we get -26.8. That represents this green vector right here. Now, if I move the x components, if I put them back where they were originally along the x-axis, I can see that if I add them together, if I take the 17.1, which is the first x component, and 22.5, which is the second x component, if I were to add them together, that's going to give me the total x component, and that works out to be 39.6. Now from our diagram, we had estimated that the total displacement had an x component of about +40. We can now see our more accurate calculation gives us +39.6, so very close to our estimate. But doing the calculation this way gives us a more accurate result, and it's much quicker than having to draw the diagram accurately and in detail. So this method of adding vectors, where we calculate the x components of the individual vectors and then total them up, this is known as the component method. And of course, we'll do the same thing for the y components. We calculated that +47 was the y component for the first displacement. The second displacement had a y component of -26.8. If we add those two components together, the total is going to be +20.2, which again is really close to our estimate of +20 that we made from the diagram. Now, if we want to know what the magnitude and the direction of the total displacement are, we can convert this vector from Cartesian form back to polar form, just like we learned in the last lesson. The x and the y components represent the adjacent and the opposite sides of a right angle triangle. To calculate the magnitude, which is the hypotenuse, we're going to use the Pythagorean formula. I'm going to use 39.6 for the x component, 20.2 for the y component. I'm going to plug those numbers into the calculator. I'm going to get about 44.4 for my magnitude. And again, we can compare that to our estimate that we got from the graphical method, and you can see again that it's really close. You'll also notice that I've been typing in more than 3 significant digits on my calculator. I'm doing this just to make sure that I don't introduce any rounding error into my final answer. To calculate the direction of the displacement vector, we're going to use the inverse tan formula. So we're going to type in the y component, again 20.2 meters, divided by the x component of 39.6 meters. And we're going to allow the calculator to figure out the direction for us. Rounded to 3 significant digits, you can see it's 27.0, which is the same angle that we measured with our protractor. Now let's look at a second example of adding vectors. Suppose a book is sliding down a slippery ramp, and it's acted upon by 3 forces. There's a force of gravity, let's say it's 5 newtons, and it's going to be directed at -90 degrees, which is straight down. The normal force is 4.83 newtons, and it's directed at +75 degrees. Now on a horizontal surface, the normal force and the gravity force are balanced. The normal force would be directed straight up at 90 degrees. Because it's on a ramp, the normal force is tilted to a direction of 75 degrees. So that's 15 degrees difference than straight up, which tells us the steepness of the ramp is 15 degrees. And the third force is the friction force, and we're told that it's 0.6 newtons with a direction of positive 165 degrees. You'll also notice that that's 15 degrees off from what it would be on a flat or horizontal surface. If it was on a horizontal surface, friction would be directed to the left, which is 180 degrees, and because we're on a 15-degree ramp, the direction of friction is 15 degrees off from 180. Now, if we wanted to calculate the acceleration of the book as it slides down the ramp, we would use Newton's second law, which states F net equals mass times acceleration. So F net means we have to add the three forces together to figure out the total force. And just like with displacement, we can't just take the 5, the 4.83, and the 0.6 and add them together and say that's the net force, because these three forces are all in different directions. The diagram we've got here is the free body diagram. It's illustrating the three forces acting on the object. If I wanted to graphically add these three vectors, I would need to draw a vector diagram. The main difference between the vector diagram and the free body diagram is that in a vector diagram, we must draw the vectors in a tip-to-tail fashion. If we were going to add the vectors graphically, we would need to make a careful drawing using a protractor, a ruler, a compass, to make sure that all our magnitudes and directions were accurate. In order to save time, I'm just going to let the computer draw the vector diagram for me. So first of all, we've got the gravity force, 5.00 newtons, negative 90 degrees is straight down. So we'll illustrate that, taking the origin for the tail of the first vector. The normal force is 4.83 newtons, so that's just a little bit shorter than the gravity force. And it's going up with a direction of 75, so that's about 15 degrees off from straight up. And then finally, the friction force is 0.6 newtons, so it's much smaller than the other two, and it's directed at 165 degrees, so back to the left and a little bit up. So we're going to draw those three forces in a tip-to-tail fashion, and just like we did for displacement, the net force, or the resultant force, would be a vector drawn from the tail of the first vector, which is at the origin, to the tip of the last vector. So the net force is going to look something like this. The reason it's so small is because the normal force and the gravity force almost, but not quite, cancel each other out. So we're left with a relatively small net force. Now, if we had drawn this accurately with a protractor and ruler and so on, we could measure the net force off of the diagram. What we're going to do instead, because it's much quicker and also more accurate, is we're going to use the second method. We're going to use the component method to add these vectors. So I'm going to start by making a table. I'm going to have one column for my x calculations and one column for my y calculations. The whole idea behind the component method is that we're going to do the x and the y calculations independently of each other. I've labeled the three forces in blue, and then I want to total those three forces to get the net force. The first thing we need to do is to convert these three vectors from polar form into Cartesian form. And just like the last lesson, just like the example we just finished doing, we're going to use the cosine equation to calculate the x component, and we're going to use the sine equation to calculate the y component. So to start with, I'm going to take my force of gravity, which is 5 newtons. I'm going to plug those numbers into the cosine formula. I'm going to go 5.00 newtons times the cosine of negative 90, and I get 0 for the answer. And I'm going to do the same thing, but I'm going to use sine instead of cosine to get the y component, and that's going to give me negative 5. According to my calculator, the components of the gravity force are 0 for x and negative 5 for y. And that kind of makes sense because the force of gravity is going straight down the negative y-axis, which means it's not going to have any x component at all. The entire 5 newtons is in the negative y direction. Okay, let's look at the second force. The normal force is 4.83 newtons. The direction is 75 degrees. So we're going to use the same formula. We're going to type in 4.83 times the cosine of 75.0. And that gives us an x component of 1.25 according to the calculator. And then we'll type the same thing, but change the cosine to sine to get the y component, and that's going to be about 4.67 newtons. So that represents the normal force. And then finally, we'll do exactly the same thing for the friction force. Once again, we get out our calculators, we type in 0.600 for the force times the cosine of 165 degrees. We do exactly the same calculation, changing cosine to sine to get the y component. So according to my calculator, these are the x and the y components for all three vectors. Now that we've converted all three force vectors into Cartesian form, now we can do the calculations independently. So we're trying to calculate the total force. So we'll do the x calculation first. We'll add the x component of gravity, which is just 0, the x component of the normal force, and the x component of the force of friction. We'll do that on the calculator, and that will give us our total x force. Then we'll do exactly the same thing in the y direction. We'll add the three y components of the forces, and the calculator will tell us what the total is. Now that we've totaled the x and the y components, we can compare the results to our vector diagram. So the x component is just under 0.7 newtons, which tells us that this red arrow representing the net force, the tip of the vector should be at around 0.7, reading it off the x-axis. And then on the y-axis, the y component is negative 0.179, so the y-coordinate of the tip of the vector should be just under negative 0.2. Now that we've completed the calculation in Cartesian form, if we want to express the answer, if we want to write the net force in polar form, just like we learned last lesson, we're going to use the Pythagoras formula. We can take our x component and our y component, we can plug those numbers into the Pythagoras formula, and that will tell us what the magnitude of the force is. So according to my calculator, the net force has a magnitude of 0.694 newtons. To calculate the direction of the net force, we'll plug the x and the y components into the inverse tangent formula. And according to my calculator, rounded to 3 significant digits, that's going to be negative 15.0 degrees. And that makes sense because we said at the beginning of this question that our ramp was inclined at 15 degrees. It sloped at 15 degrees. So we expect the object is going to accelerate down the ramp, which should correspond to a direction of negative 15 degrees. Now let's look at one final example. Suppose a car is moving east at 20 meters per second. It accelerates around a curve in the road. The car exits the curve after 5 seconds with a velocity of 25 meters per second northeast. What was the car's acceleration? Well, to calculate acceleration, we need to use the definition, the formula, which is final velocity minus initial velocity divided by time. If this had been one-dimensional motion, we would simply take the numbers given in the question and we would plug them into the formula. We would plug in 25.0 meters per second for the final velocity minus 20.0 meters per second for the initial velocity. That would give us 5 meters per second on the top. We would divide by 5.00 seconds, and that would give us 1.00 meters per second squared. So that was for one-dimensional motion. The problem with this question is that the initial and the final velocity are in different directions. The initial velocity is east, the final velocity is northeast. Now, the graphical method that we've been talking about really only works when we're adding vectors, which is not the case here. We've got a formula that we need to evaluate that involves subtracting two vectors and then dividing by a scalar. So the graphical method isn't really going to work for this one. We're going to go straight to the component method. So I'm going to make my chart here. I've got one column for my x components. I've got another column for my y components. I've written down the formulas to remind myself that I calculate the x components with the cosine and I calculate the y components with the sine. And I've written down the two velocity vectors. The initial velocity is 20.0 meters per second. East, typically east, we take to be 0 degrees. And then the final velocity is 25.0 meters per second. The direction is northeast. No angles given, so we assume that means it's exactly halfway between north and east, which would give it a direction of 45 degrees. The idea of the component method is that we're going to express all of our vectors in Cartesian form as an x and a y component, and then we're going to perform the calculations for x and y independently. So let's start by converting the initial velocity into Cartesian form. Now, because the initial velocity has a direction of 0 degrees, that means it's straight along the x-axis. So we don't even really need a calculator to determine the Cartesian components. Because that 20 meters per second is along the x-axis, the x component is going to be 20 and the y component is going to be 0. Now for the final velocity, we will need to use the calculator. The x component is going to be 25.0 times the cosine of 45, which is 17.7. And then we do the same calculation, changing cosine to sine. Turns out we get exactly the same number. That's again because 45 degrees is exactly halfway between x and y. So we're going to get the same component for both x and y. Once we've converted our vectors to Cartesian form, we can use the equation to evaluate the acceleration by doing the x and y component calculations independently. So starting with the x component, we're going to calculate the final velocity. We're going to type in 17.7 for the final velocity. We're going to subtract 20 for the initial velocity, and then we're going to divide by the time, which is 5.00 seconds. And this gives us an acceleration for the x component of negative 0.464 meters per second squared. Now notice that the 5.00 seconds does not have components. Time is a scalar. Only vectors have components. So the 5.00 seconds, that's the time we would use in the calculation for both the x and the y components. Now let's look at the y calculation. So same formula, different numbers. The final velocity is 17.7. The initial velocity this time is going to be 0 for y, and the time is going to be 5.00 seconds. And that's going to give us a y acceleration of positive 3.54 meters per second squared. So these two numbers represent the acceleration expressed in Cartesian form. If we want to convert the answer to polar form, as always, we would use the Pythagoras formula in order to calculate the magnitude of the vector. Typing in the 0.464 for the x component and the 3.54 for the y component, we end up with 3.57 meters per second squared for the magnitude of the acceleration. And then to find the direction of the acceleration, we're going to use the inverse tan formula. 3.54 is going to be the y component. Negative 0.464 is going to be the x component. The calculator gives us negative 82.5 degrees for the direction. We've got to be careful here. The x component of the acceleration vector is negative, which means the acceleration vector is pointing to the left into the second or the third quadrant. So as we learned in the last lesson, whenever that's the case, you have to add 180 degrees to the answer that the calculator gives us. So the correct direction is actually 97.5 degrees. Looking at the acceleration, 97.5 degrees is kind of up and a little bit to the left. And that sort of makes sense because if the car is moving in a curve, as we learned in the uniform circular motion chapter, the force has to be directed towards the center of the circle. Now, technically, this isn't uniform circular motion because the speed is actually not constant. The car is picking up speed from 20 to 25 as it moves around the curve. So the force won't be exactly towards the center like it is for uniform circular motion, but it should be in the general direction of the center of the curve. Now, sometimes you might have to do some algebra before you can evaluate the equation. So, for example, I could have given you the acceleration as part of the question and asked you to calculate the final velocity. If that were the case, you would just do the algebra. You would isolate the final velocity exactly as you would for a one-dimensional problem. And then you would do the calculations for x and for y independently. Now, I've labeled my columns Vx and Vy. Technically, only the first two rows here are velocities. The third row is actually acceleration, so I should probably just change them to x and y. Now that concludes this lesson. Here's some summary notes coming up.